we're given percentages of these elements, and we're asked to use that information to turn that into a formula. So a formula of a compound is an intensive property. It doesn't matter how much of that compound you have. You can have a gram of it, you can have 1,000 grams of it. It's going to have the same formula. So when you're given percentages, the easiest quantity to use is 100, because percent means per 100. All right, let's assume we have 100 grams of this compound, because that'll make our calculations easier. And again, it doesn't matter how much you have, you're going to get the same formula. So why not use the easiest numbers to work with? So for the oxygen component, if we had 100 grams of this compound, the oxygen component would make up 94.1 grams, and the hydrogen component will make up 5.9 grams. Again, we're assuming we have 100 grams of it because it doesn't matter how much of it we have. It's just an easy way to turn percent into grams. And the reason we want to do that is because we want to turn grams into moles. And the reason we want to do that is because in the formula, when you have the subscripts for H and O, these subscripts can be interpreted as mole ratios. So we want to get moles. How do we convert grams to moles? We need a conversion factor with grams on the bottom and moles on the top. We use the molar mass as our conversion factor. Molar mass information is given to you on the periodic table. The molar mass of oxygen is 16.00 grams if you had 1 mole of it. That's how much mass of oxygen you would have. Similarly for hydrogen, the molar mass is 1.008 grams. Put that on the denominator and moles on the numerator to cancel out. 94.1 divided by 16. If we had 94.1 grams of oxygen, we would have 5.88 moles of oxygen. Let's do the same for the hydrogen. If we had 5.9 grams of hydrogen, we would have 5.85 moles of hydrogen. Now you can see the mole ratios are almost identical, which means it's just a 1-to-1 ratio of hydrogen and oxygen. The empirical formula is HO. Now let's move on to B. All right, you try the same for part B. Let's assume we have 100 grams of this compound, and then that'll allow us to turn these percentages directly into grams. For the mercury component, that means we'll have 67.6 grams of mercury. For the sulfur component, we'll have 10.8 grams of sulfur. And for the oxygen, we'll have 21.6 grams of oxygen. Next, let's turn these into moles using the molar masses from the periodic table. Let's punch these numbers in our calculator. 67.6. If we had that many grams of mercury, let's divide that by the molar mass, 200.59. We would have 0.337 moles of mercury. If we had 10.8 grams of mercury, then we would have 0.337 moles. I'm sorry, did I say mercury? I meant sulfur. Sulfur. That's mercury. And then if we had 21.6 grams of oxygen, we would have 1.35 moles of oxygen. So now we want to take the lowest result, or the smallest result, and see how many times it goes into all the other results. And the reason is, right now we have an empirical formula of mercury, Hg, 0.337, sulfur, 0.337, and oxygen, 1.35. And this is not a valid formula. Can't have decimals in the subscripts. So we're trying to get rid of these subscripts. And to do that, we can see how many times the smallest result goes into each of the other results. And that will guarantee that at least one of our decimals will turn into a whole number. All right, so anything in itself is going to be 1. So Hg mercury, we have a mole of 1 right now. And same thing with sulfur. And 1.35 divided by 0.337, and that's going to go in 4 times. So because our results give us whole numbers here at this step, that means that's our empirical formula. Now, if it didn't give us whole numbers, we will have to multiply through until we get the whole numbers. So our answer here is HgSO4.